Thank you, Ekaterina. Can everyone hear me?
And can I ask you also to make a full screen of your...
Okay, right. But you can see my screen?
Yes, we can see your screen and we can
Okay,
hear you well.
okay, that's great. Okay. Well, thanks to the organizers for giving me this opportunity to give this talk today. Um, so I'm going to talk about linear dynamical quantum systems, directions and opportunities. I intended this talk to be more of an exposition rather than a technical talk. And the outline of my talk today will be these 4 points. So we'll begin with an introduction to linear quantum stochastic systems. And then one focus of the talk will be on new directions and open problems. So we'll talk about one new direction, which I've been starting to look at, which is system identification for linear quantum systems. And then the problem, and then I will talk about a new direction of infinite dimensional linear quantum systems. And I will conclude my talk with some concluding remarks. So let's start with the first point, introduction to linear quantum systems for those who may not be familiar with these kind of systems. So let's begin with the classical setting. So probably most of you are familiar with this kind of equation. So this is just a linear stochastic differential equation in state space form. So here X is the state, U is a control signal, and W here is just a winner process. So this kind of equation, so YT here is the output of the system, and U is usually this is a control input. So this class of models, they're important in modern control theory, as they form the basis for the Kalman-Bucy filtering and stochastic filtering theory, and also stochastic optimal control theory, in particular linear quadratic Gaussian or LQG control. Now there is an analogous class of quantum stochastic models that have linear dynamics, like in the classical case. This is linear in dynamics in the Heisenberg picture. The difference is that instead of having complex of real numbers inside vectors such as xt and yt, we have operators that do not necessarily commute. So these linear quantum, so I call them linear quantum stochastic systems. So they model various linear quantum devices that is found in applications, for example, in quantum optics, optomechanics, and superconducting circuits. So for example, they model optical cavities, linear parametric amplifiers, so both optical and superconducting, and optomechanical systems such as gravitational wave interferometers. So I will next describe what I mean by these linear quantum stochastic systems in terms of the dynamics. So before I get onto that, I'll just introduce some of these concepts that we'll encounter again as I proceed with this talk. So I'll introduce these singular operators, which are denoted by BJT and BK star T. So basically these are annihilation and creation densities, and they satisfy these singular commutation relations. So basically you have BJ and BK star, so they satisfy this commutation relation. So it's a delta commutation relation when the J is not equal to the K, and the commutators of all the other quantities are equal to 0. So by this being singular, it's more convenient to work with the integrated version of these processes. So this is what I denote by this capital A J. So these are just the integrated versions of these densities. So this is a structure of a general linear quantum stochastic system. So basically, you have some input fields. So this A1 up to AN, they're the integrated processes that I just introduced in the last slide. And for each process, AJ, you can write as a sum of two self-adjoint components. So for example, A1 is W1 plus IW2. So these are, the W1 is called the amplitude curvature, and W2 is called the phase curvature of the field. So in a linear quantum stochastic system, you have these M boson fields coming in. They can interact through a passive static network, which is denoted by S. So this is nothing more than just a complex unitary matrix. So after passing through the static network, you get it as the output of the network. Again, some boson fields as transformed versions of the input fields. And these output boson fields from this optical network can go on to interact with multiple harmonic oscillators. So here, this vector X consists of the position and momentum operators of your oscillators. So for example, Q1, P1, the position and momentum operators of the first oscillator. And then after interacting with this oscillator, these fields P1 to Pm, they leave the system as output fields, and this is denoted by capital Y1 up to capital Ym prime. So technically, there should be the same number of output fields that are input fields, but written here with an index M prime, which can be less than M, because you might not be interested in all the fields that appear at the output of the system. So you might only be interested in some subsets of the output field. So, so this is basically the structure of a general linear quantum stochastic system, and it's parameterized by 3 parameters. So you have the Hamiltonian, which is quadratic in this vector X, where R here is a real symmetric matrix. And then we have an operator L, which is a linear combination of elements of X. So this is what's called a coupling operator. So it describes the coupling of your harmonic oscillators to these fields B1 up to Bm. And as I mentioned before, we have a complex scattering matrix S, which is unitary. All right, so when you write down the equations for the vector X in the Heisenberg picture, so there's a unitary interaction that describes there's a unitary propagator that describes the interaction of the system and the fields. So when you write down the equation for the motion of X in the Heisenberg picture, then what you will get is a linear quantum stochastic differential equation, which will be abbreviated as QSDE, that is of this form. So this looks just like the equations for a classical linear stochastic system. The main difference is that now with the elements of X and Y, they're operators. Here we have WT. So WT is just the vector of input quadratures to the system. So again, this comes from this decomposition of your annihilation operator into these 2 components. And so we put them together in this vector WT. So W1, W2. So W1 is the amplitude quadrature of the first field, and W2 is the phase quadrature of that field, and so on to the last components. And YT consists of these components, again, quadratures, pairs of quadratures of each of the output fields. So now these being operators, XT and YT, they don't, not all elements of these vectors commute, and they satisfy these commutation relations. So the commutator of XT with its transpose, which is defined by the term that I have on the right-hand side, that's going to be given by this constant 2I times Jn. So this Jn is just it's a skew symmetric matrix, which is the tensor product of the identity with this 2 by 2. This is the X operator, if you will, the Pauli X operator. And so in the same way, we have also the commutators for the differential of the noise, WT, the quadratures of the noise. And so this is given as, it satisfies a similar commutation relation as X. And then we have this, so the sum of this, the product of the differentials plus its transpose, that gives us a term 2F. And this is basically this matrix F is covariance matrix for this operator when we take it to be a Gaussian state. So this F is a real symmetric matrix. And because of the Heisenberg uncertainty principle, it satisfies this constraint where F plus I times this matrix Jm, that must be positive semi-definite. So, so in a linear quantum stochastic system, even though the quadratures Q1, P1 up to Qn, Pn all evolve linearly, these are the only ones that evolve linearly. So in general, the other operator will not evolve in a linear way. So one distinction from the classical setting is that the matrices A, B, C, D, they cannot be arbitrary for linear quantum system, and this arises from the fact that it's a quantum mechanical system, so it must satisfy constraints that are set by quantum mechanics. So we don't encounter this kind of restrictions on or constraints on A, B, C, D in the classical setting. So because of this, we can have a notion of physical realizability for linear QSDEs. So not all linear QSDEs will represent the dynamics of a quantum mechanical system. And so, and then so physical realizability singles out the linear QSDEs that do represent a linear quantum mechanical system. So these are the conditions that must be satisfied by the matrices ABCD. So if these three conditions are satisfied, and then the linear QSE will represent some bona fide linear quantum system. Now, one important property of this linear quantum system is that they preserve Gaussian states. So if the initial state of the oscillator and the boson fields are all in a Gaussian state, the linear dynamics ensures that the oscillator state is going to be Gaussian at all times. So you will find that these linear quantum systems are important for the realization of quantum information processing using Gaussian states. So now with this system, you can so you can take the commuting components of the output YT. So if we go back to this picture I had earlier, so we have these components Y1, Y3. So the odd numbered components of the small y, they all commute, and also the even ones, they commute. So you can measure these simultaneously by a process called homodyne detection. And then you can use this to construct a mean square optimal estimate of x. So x you can't observe, you can only observe y. And through observing y, you can generate a mean square optimal estimate of x. So this is what's called quantum filtering. So it's the quantum analog of stochastic filtering theory. Now, if we consider the linear quantum stochastic systems in this talk, and all the input fields are in a Gaussian state, this leads to a quantum version of the Kalman-Bucy filter for this class of systems. So this was pioneered by the late Slava Blavkin. And based on this quantum filtering theory, you can also have a quantum version of the linear quadratic Gaussian control for linear quantum stochastic systems. So this was also something which originated from Blavkin's work. But beyond that, you can also consider other control problems for linear quantum systems. And there is also a network synthesis theory. So if you have a physical realizable linear quantum system that satisfies the constraints that I showed earlier, then there is a theory that shows how you can systematically build this corresponding physical system that has the dynamics of that linear quantum system. So as with a classical linear system, we can also define a transfer function for linear quantum systems. And so this is given by this expression here. So it's a complex valued function that's constructed from the ABCD matrices. And I will get back to this later on. So as I mentioned, one of the intention of this talk is to introduce some new research directions. So one direction is system identification for linear quantum systems. So system identification is a technique that's important in engineering, and is used for inferring a model for a black box system by observing the system's output response to known inputs. So for example, you may be interested in a system, but you don't know exactly what it is. And so you try to build a mathematical model for this unknown system by sending in some inputs to the system and observing the outputs. And then based on the input-output data that you have, you try to infer a model for what's inside your black box. So typically this is done using just a single stochastic input-output record that you obtain from the system. So for example, you can send a particular input to the system, and then you do homodyne detection, you measure the output, and then based on that data, you try to build a model for the black box that you're interested in. So for example, a standard text about system identification for classical stochastic systems, this is a book by Leung. Right, so I will now just give an overview of some known results about system identification for linear quantum systems. So early work on this by Gutta and Yamamoto and Levitt and Gutta, so they're in these references down here, have shown that if you use a coherent state input to your system and you observe the output response, then you can identify this matrix ABCD for your unknown system up to a similarity transformation. So you can't get exactly what the ABCD matrices will be, but you can identify them up to the similarity transformation. So with this matrix T here is a real invertible matrix. So this was one of the early results for system identification of linear quantum systems. Okay. Right. Now, another method that's been proposed is system identification through the power spectral density of the linear quantum system. So the power spectral density, which is abbreviated as PSD, of the output YT of a linear quantum system is given by, it's defined as in this way. So it's a product of G minus S is a complex variable, times F. So F is the covariance matrix of the input, and times G transpose. So G here is just the transfer function of the system that I introduced earlier in this slide. So, so if we have information about the power spectral density of the output of the linear quantum system, then we can do identification based on that. So if we choose the input to the system, so we have freedom to choose this. So remember that, known inputs, so we can engineer the input that we will send to the system. So if we choose the input to be a zero mean Gaussian state with a covariance matrix F, so this matrix here, such that this F is not invariant under symplectic transformation, then in this this joint work that I did with Matthew Levitt and Marilyn Gutta, we showed that from knowledge of this output power spectral density, you can identify the matrix ABCD for your unknown system up to a similarity transformation if the system is globally minimal. So globally minimal here means that so if you have a globally minimal model, that means that there is no smaller model in the sense that it has a smaller number of internal oscillators that have the same PSD. So if you identify a globally minimal model for a given PSD, then the ABCD matrix can be identified up to a similarity transformation. So, but there is an open problem because this is a, it's a fundamental result, but there's no algorithm yet to empirically estimate the PSD and identify a model from a single input-output observation data. So this is an open problem from this work. So another work that I was involved in with Nina Amini and my student Jen Chen was to develop a method for identifying a system based on coherent inputs. So as I mentioned earlier, this is already a known result about that you can identify the ABCD matrices up to a similarity transformation using coherent state inputs. But in this work, we developed an empirical method to do that. So this was based on data from the system, which is just a continuous measurement of commuting quantities of the output YT. So for example, you can measure the commuting amplitude quantities of the M prime fields, or you can measure the phase quadrature of the M prime fields. And based on this data, you have a single measurement, and so you have a single record of input and output to your system with a known input, which is the coherent state that you put into the system. And then you can, this algorithm will identify a model for your unknown system. So it has two steps. So the first step is to estimate a classical linear stochastic model using a classical identification system. So this classical linear stochastic model is one that need not meet the physical realizability conditions for that's required for a linear quantum system. And then the second step, you solve a particular optimization problem to find a physically realizable linear quantum model, which is close to the one that was identified in step one. So this optimization problem will produce a set of ABCD matrices that will satisfy the linear, the physical realizability constraint. So this work was under the assumption that D is known. But this assumption needs to be relaxed, and so that's work that's currently being investigated, how you can remove this assumption. Okay, so next I would like to introduce another possible direction for research. So the class of linear quantum systems that I've introduced, they're finite dimensional quantum system in that the vector xt consists of a finite number of operators. So I'm going to motivate why you want to study an extension of this to the case where you have an infinite dimensional linear quantum system. So you have an infinite number of degrees of freedom. And the motivation for this is a class of optical quantum memories that called photon echo memories that was have recently been developed. So these are memories that can not only store the amplitudes of a quantum state, but actually can also store the temporal profile of the optical pulse that was used to encode the quantum information. So there are many types of photon echo memories, and one type, as for illustration, is what's called a gradient echo memory, or GEM. So this is a basic structure of a gradient echo memory. So it has a certain length, the memory. You have a pulse coming into the system. And the way it works is that so it's basically, you have a cloud of two-level systems, and you apply a magnetic field gradient across the memory. And so that creates, along the length of memory, you will have a different separation of energy of the two-level system at different positions in the memory. So when you, in this picture here, as you go to the right, the separation of energy levels between the excited and the ground state becomes smaller. So what happens is that, and when an optical pulse comes in, different frequency components of a pulse will get absorbed into at different locations in the memory. So this is basically storing the frequency components of the memory. And then so that will store the pulse inside the memory. And then to read it out, what happens is that you swap the gradient. So you swap from a negative gradient to a positive one. And what will happen is that the pulse that was stored inside memory will eventually come out on the right-hand side. So this picture here I've taken from this preprint from Hendra et al. So they discuss a model for this gradient echo memory. So under certain assumptions, this gradient echo memory can be modeled as using infinitesimal slices along the length of the memory. So you imagine here that you can cut this into very small pieces, and these pieces are in a cascade or series connection. So an input field comes in, it interacts with one slice at a time. And so after interacting with this slice, it gives an output field which continues and interacts with the next slice and so on. And so this is in storage mode, and when you read out, it goes the other way around. So this model for the gem was developed in this paper here. So for an infinitesimal slice at position X, we can associate a field operator Bx and B star X. These again annihilation and creation densities along the length of the gem, and they satisfy this singular commutation relation that we saw earlier for the boson fields, but now these commutation relations are in spatial position rather than in time. So this model that was proposed is a genuine quantum model, and what happens is that without going into the details, what they did here is that they arrive at a linear quantum dynamics for the gradient echo memory, but where now the vector xt is replaced by an infinite dimensional object in this model. So the current treatment of this is mainly at a heuristic level. So the scope for developing a general and systematic theory for these types of infinite dimensional linear quantum systems. So as I mentioned earlier, the GEM is just one type of photon echo memory, but there are a whole class of these memories, and I expect that similar models can be developed for the entire class of these photon echo memories. So that brings me to the end of my talk. So just to give some concluding remarks. So what I've done in this talk is to just give a brief introduction to linear quantum stochastic systems as quantum analogs of classical linear stochastic systems. So they represent a large class of linear quantum devices that are found in practice and in laboratories, including gravitational wave interferometers and optical quantum memories. And so I mentioned some new research directions and open problems in system identification for linear quantum system, and also for developing a theory for infinite dimensional linear quantum systems. During the talk, I've pointed to a few references, but there might be a few more on this class of system that might be of interest. So I've listed them here. And with that, I thank you very much for listening to this talk.
Okay, thank you for such an interesting talk. And we have about 5 minutes for questions or comments. So please, if
so may I ask you a question?
Yes.
About
Yes.
system identification. So in the beginning, you showed the scheme with matrices where Hamiltonian was present and the matrix L was also there.
Mm-hmm.
So can you identify the Hamiltonian or some other derivative from that Hamiltonian, say unitary?
Yes, so let me just get back to, yeah, so something which I didn't say in this talk was that, so let me just go back to this slide.
Yes, this is figure.
Yeah. So we have these three parameters, H, L, and S. So basically this H is determined by this symmetric matrix R and also this complex matrix K. So, you know, there's a one-to-one relationship between R, K, and S to the A, B, C, D parameters. So if you have an A, B, C, D, which satisfy these constraints, then you can uniquely associate that with an H, K, and S. So they're one-to-one. But in identification, as I mentioned in the later slides, is that you typically, when you try to identify based on input-output data, you cannot determine A, B, C, D, but you can only determine A, B, C, D up to a similarity transformation. But because of this one-to-one relationship between A, B, C, D and the parameters R, K, and S, that means that you can only identify these parameters also up to a similarity transformation. You can't identify them uniquely.
Okay, thank you. And I have also the second question related to the first one. So you have passive optical elements, which means that your environment is in principle infinite dimensional. But you also mentioned some global minimality. So do I understand correctly that you replace infinite environment by some finite collection of modes?
Okay, so maybe let's go back to, so global minimality is means the following. So if you have a power spectrum, so if the power spectrum is rational, so it comes from some linear system, it could be a classical linear system or a quantum linear system, then, you know, so that you can associate a transfer function to that power spectral density. Now, with global minimality here means that, you know, if you have a power spectrum which is globally minimal, so I mean, no, not the power spectrum, but if you have a realization from the power spectrum which is globally minimum, so for a particular power spectrum, there could be many transfer functions which satisfy this relationship. Yeah, this is not essentially unique, right? Now, but if you have a global minimum realization of this power spectral density, that means that any other G which satisfies this relationship cannot have you know, the number of oscillators in that system cannot be less than one, which is already globally minimum. Does that make sense? So it relates to, so it relates to this vector X. So this X has a finite number of elements. So when it's globally, when you have a transfer function, which is a globally minimal realization of power spectral density, it means that you will find no other realization of that power density for which the vector X has less elements than one which is globally minimal.
But in principle, your matrix is A, B, C, D as a finite dimensional or
this is dimensional? In this one, they're all finite dimensional. But in this later one, where we talk about this optical memories, they will be infinite dimensional.
Okay, thank you.
Thank you.
Okay, if we have no any questions, then let's thank you the speaker. So it was an interesting talk.